Hello. Hi everyone. I'm Aman and today I'll be presenting my team's work on tracking socio-economic development in rural India over 2 decades using satellite imagery. So let's get started. We begin by asking how to track development in rural India. An obvious answer to this question can be using censuses and surveys. However, these are too infrequent as censuses are conducted once in every 10 years and surveys are conducted once in every 5 years. Secondly, they can be inconsistent in terms of village or district boundaries that they use or the parameters that they took. A rather reliable source of development, tracking development can be satellite imagery, in which the data is available at finer temporal and spatial scales, and they can also serve as to build proxy indicators for socioeconomic development as proven in past literature. In this study, we wish to build a temporally stable classifier which can produce output for different years and track changes that happen during this time. So next we'll further motivate the need for having a source of monitoring development by discussing its advantages. Firstly, it helps in identifying the relative needs in different areas, thereby promoting optimal resource allocation. Secondly, it helps in understanding factors that shape development of villages. Lastly, it makes the decision-making process more informed and driven. We'll now look at how we use the census data in our work. Census data is available for the years 2001 and 2011, from which we use the 2011 values as the ground truth. An important point to note here is that satellite imagery data is available from 2003, and since it is close to 2001 census year, we use this data to evaluate our estimate of development against the 2001 census data. Next, to achieve temporal robustness, we choose features that give best accuracy when trained on 2011 and tested on 2001 data. Finally, we use these sets of features to train our final model and generate outputs for 2003 and 2019. Next, we look at the process of creating development indicators from census data. Here, we'll be focusing on fuel for cooking as an example. In the census, each row represents a village and the percentage of households using various fuel types. We categorize these fuel types into three stages: rudimentary, intermediate, and advanced, based on development levels. Then we transform the census data into a table showing the percentages of household in each village using these three categories of fuels. Further, we perform k-means clustering on the villages, representing them in 3D space as a tuple of percentage household in each category. From the clustering, we obtain three bins, namely level 1, which use predominantly rudimentary fuels, level 2, which use predominantly intermediate fuels, and level 3, which use predominantly advanced fuels. We perform the discussed procedure of extracting development indicators for five variables, namely asset ownership, main source of water, literacy, fuel for cooking, and bathroom facility. We also define a composite index called the Aggregate Development Index or ADI of a village as the numerical sum of levels of development. We use this index as the measure of socio-economic development of villages throughout our work. Now we'll discuss about the availability of satellite imagery data. In our work, we use Landsat 7 satellite imagery. As discussed earlier, it is available since 2003. It has a revisit time of 16 days and a resolution of 30 meters. We also obtain village shape files from NASA SIDAC. We obtain village images after performing some pre-processing and then cropping village shape. A sample image is shown here. We begin the process of training models by using a direct CNN classification as our first architecture. We train a vanilla ResNext 50 CNN model to predict levels of development indicators. We also perform occlusion and gradcam analysis on trained CNN weights. For example, in this village image, we notice that model focuses more on the build-up pixels, which is consistent with our intuition. We also use additional features to make better predictions. These include CNN features of neighboring villages, number of households data from census, nightlight data. We use nighttime luminosity time series to create nightlight features for villages. We first perform Otsu thresholding to identify economic hubs within districts. We then map villages to these hubs based on distance, size, and brightness. You can see the economic hubs within the districts of India in the image on the right. We will now discuss our second architecture, which begins by generating the rich feature set previously mentioned. From this, we select features that ensure temporal robustness. Using this final feature set, we train three regression models to predict the percentage of household using rudimentary, intermediate, and advanced fuel categories, as shown in these three boxes. We then employ a pre-trained discretizer to estimate village development indicator level. We also train a third architecture that uses the exact same pipeline, just the CNN in the first stage is used to produce a continued value output of percentage of household instead of categorical outputs. We now compare the performance of the three architectures. This table shows the root mean squared error and its normalized values for architecture 1, 2, and 3. Architecture 2 seems to be performing the best, and the approximate error in all three models is around 10%. This plot below shows the histogram of village ADI over the years. We can notice the peak density of ADI shifting towards right over the years, which indicates development. We next hypothesize that developed villages tend to be closer to economic hubs. To validate this hypothesis, we built separate OLS models for the years 2003, 11, and 19. Having ADI as the dependent variable and distance to closest economic hub as the independent variable. Observing the plot and the slopes, we notice a statistically negative relationship between village ADI and distance of village from the closest economic hub, thus validating the hypothesis. We can also notice the plot on right, which shows the cumulative density of distance to closest economic hubs. We notice that curve shifts leftwards over the years, indicating that the distance to nearest economic hub is decreasing, thereby promoting development. We now hypothesize that villages in economically unequal districts tend to develop faster. We first define the Gini coefficient of districts as the measure of inequality within the district. The Gini ranges from 0 to 1, with 0 indicating perfect equality. We perform a similar OLS model study between change in ADI and Gini. We observe that while the hypothesis remained true during the phase 2003 to 2011, the trend reversed during the phase 2011 to 2019. This interesting shift can be attributed to significant change in Indian politics in 2014 when the incumbent UPA government was replaced by NDA government at the center. This change led to difference in design of welfare and industrial policies. Next, we try and validate the Kuznets hypothesis in our context. So, the Kuznets hypothesis describes two phases of development. The initial phase, in which the economic growth leads to increased inequality, but as the country grows further, the inequality begins to decrease, forming an inverted U-shaped relationship between growth and income distribution. While the original hypothesis was framed at country level, the core idea was the interplay between economic growth and economic inequality. We wish to study this interplay at district level. For that, we use mean district ADI, which is the population weighted average of village ADI as the measure of economic growth, and Gini coefficient of district as the measure of economic inequality. We next observe the starting phase of Kuznets hypothesis. In this phase, we analyze all districts that have a positive change in ADI and a positive change in Gini. The Plots below show that in 2003 to 2011 period, the inequality increment was highest in uh, districts which have the least development. This was consistent with the Kuznets hypothesis. However, the pattern does not hold true for 2011 and to 2019 period. Similarly, in the ending phase of the Kuznets hypothesis, we analyze all districts that have a positive change in ADI but a negative change in Gini. We observe that during the time period of 2003 to 2011, the inequality decrement was highest in districts where development was the highest, which was consistent with the Kuznets hypothesis, as the inequality decreases after the development reaches a certain level. But again, the same trend doesn't exist for the period 2011 to 2019. We attempt to interpret why no regular patterns were observed during the phase 2011 to 19. This could be attributed to significant changes that occurred during this period, such as demonetization, in which countries' notes were devalued and new currency was circulated. Also, a new goods and service tax regime was introduced during this period. So in conclusion, we use the census data, satellite data, and other data sources to create a pipeline that generates temporally robust estimates of socio-economic development in rural India. We use this pipeline to make the development estimates for 3 years, namely 2003, 11, and 2019. We further analyze village development patterns over 2 decades using the generated ADI values. Source code and the datasets are available for use by others. That's the end of the presentation. Thank you all for listening.